All right, so many of your classmates are over at the conference. I was there earlier today. There's some really interesting presentations. If you've got time this afternoon, there's going to be some others, including one about Bluestone Dam, which is going to be, I think, a pretty good presentation. So if you've got spare time, I'd encourage you to head over to the basement of the Student Center. BE5 is where they're having that. Class on Friday is going to be a recorded lecture. It's going to be the second part of a discussion of the Three Reservoirs Problem. So we won't meet together in class on Friday. On Monday of next week, I'm going to ask you to show me the binder that you've put together to hold the course materials. I know that some of you use electronic methods for your note-taking. You know, maybe you're writing your notes onto an iPad. And so if you're able to show me your notes on that iPad, and like your handwritten notes and your homework assignments, basically the same kind of equivalent of collection of materials that you would have normally in a 3-ring binder, then that's fine as well. So we'll just take a few minutes at the beginning of class on Monday to do that check. And then the next homework assignment, number 3, is available now on Blackboard. It includes 3 questions related to the Three Reservoirs Problem, which is being introduced today. So after today's class, you'll be able to solve the 3rd problem, and then after Friday's class, you'll be able to solve the 1st and the 2nd problem. So on that homework assignment number 3, there's only 3 problems. The first 2, you're doing the Three Reservoirs Problem with Darcy-Weisbach as the friction method. And then the 3rd problem, I ask you to generate a Three Reservoirs Problem of your own using the Hazen-Williams friction method. And so that's what we're going to be doing today, is applying the Three Reservoirs technique and using the Hazen-Williams equation as our friction estimating approach. So any announcement-related questions? Yeah.
So if we take our notes on our computers, do we need to have the lecture slides downloaded and notes on those, or is it just like blank sheets with notes on those?
You can take your notes however you like, but I would like you to be able to show me that you've got the lecture notes and that you've got like your old homework assignments. Yeah, but you don't have to take your notes on the slides that I've provided as PDFs.
Okay.
All right. Other questions? All right. So before we get into the pipe networks, Three Reservoirs stuff, just let's take 2 or 3 minutes and talk about what if your pipe isn't circular. How do you apply these friction loss formulas to a non-circular conduit? And there are pretty commonly non-circular conduits, and in many cases they're flowing full as well. So you could have metal pipe that's rectangular or square. Here's an arch pipe culvert. This photo I took in Dubai, which is where I lived for a few years, and this is to carry runoff stormwater out of the mountains out towards the sea. They have this road with really big, you can't tell from the photo because there's nothing for perspective, but it's probably about 12 feet from the bottom to the top of that pipe. So it's non-circular. How would the friction loss formulas apply to a non-circular conduit? Well, we have to have something else besides diameter as the size parameter. And so the adjustment that we make is just to think, first of all, in terms of, remember, hydraulic radius, where if it's a circular pipe flowing full, it's just as simple as saying diameter divided by 4. But if it's a non-circular conduit, we actually have to calculate the real cross-sectional area, the real wetted perimeter. So in the case of like a square pipe, then the area would just be the length times the height, and the wetted perimeter would be 2 times the length plus 2 times the height, and that would give you the wetted perimeter. So, you know, it's no great adjustment to calculate the hydraulic radius, but we adjust the Darcy-Weisbach equation by substituting in 4 times the hydraulic radius in place of diameter. So normally Darcy-Weisbach equation just has d in the denominator, and the adjustment if you have a non-circular conduit is 4 times the hydraulic radius. And so we can make that same adjustment for the Reynolds number formula, where normally we would think in terms of diameter, Instead, we just substitute in 4 times the hydraulic radius for Reynolds number. So here, the Reynolds number is being described in terms of fluid density and absolute viscosity. If we had it in terms of the kinematic viscosity, it would be the velocity times 4 times the hydraulic radius divided by the kinematic viscosity. So the substitution is just 4 times the hydraulic radius instead of the diameter, and that can be extended to measures of relative roughness as well, where epsilon to diameter is that right-hand side axis that we use in the Moody diagram. So instead of that, we would just say epsilon divided by 4 times hydraulic radius. So all the same principles beyond that apply, and so it's a pretty simple substitution. To save time for our example on the Three Reservoirs problem, we're not going to work through this problem. I want to preserve our time to just go a little bit more slowly through the spreadsheet, but just to tell you the background of this one, we have water flowing through this culvert, and what we know is the dimensions. The 1.25 by 1.25 is what we would use to calculate the cross-sectional area and the wetted perimeter, and so you'll see that the Jane equation has been adjusted accordingly, where in the past, remember, the Jane equation would have K sub S divided by 3.7 times D. Now we've got K sub S divided by this 4 times the hydraulic radius substitution. So here is what we normally would see as D for a non-circular conduit, 4 times the hydraulic radius. And then in the other term within the Jane equation, we are calculating the Reynolds number with the same 4 times hydraulic radius. So you get the idea, I think. It's just a simple substitution, and then that allows you to calculate the effect of pipe friction on non-circular conduits. Any questions before we move on from non-circular conduits? Okay. I was sitting with a hydraulic engineer over at the technical conference, and I asked him, do you remember the Three Reservoirs Problem? And he immediately smiled. He definitely remembers the Three Reservoir Problem. This is just kind of like a classic among hydraulic engineers, and I guess anybody who's taken a hydraulic engineering class. It's kind of in certain ways like a brain teaser. And the problem is that it's obvious which way the flow is going out of the high reservoir. So reservoir B, by inspection, by just pure logic, we know that the water is going to go from B towards D. D is the junction where 3 pipes are coming together. Because, water flows from high to low. Okay? So it's obvious that the water is going to be flowing into reservoir C. But the problem, the uncertainty, comes with what's happening to the middle reservoir. So let's take it to the extreme. What if the middle reservoir was at the same elevation as the high reservoir? So what if reservoir B and A, both of the water surfaces were at the same elevation? Then what direction would water be coming either into or out of this reservoir A if it was the same height as B? It would be going out. Yeah, obviously, if both of the reservoirs are at the same elevation, then the water would be going out of the middle reservoir. Okay, so the other extreme is, what if reservoir A had the water level down as low as the water level for reservoir C? Then the water would be flowing in to reservoir A. But as you can see, it's somewhere in between. And so we're not exactly sure whether the water is going from D to A, or if the water is going from A to D. So in other words, some of the water could be coming from B and going into A, or some of the water could be going from A into C. And so, think about a horizontal pipe. If you've got a horizontal pipe and we're connecting it to a reservoir and the two water surface elevations are the same, there's not going to be any flow between the two reservoirs if the two elevations are the same. But now, what if the water level is low on this side? If the water level is low on one side, then the water is going to flow from where the energy is high to where the energy is low. So the same thing is true in this whole analysis. What we need to do is establish how much energy there is at D. And once we figure out how much energy there is at D, the total energy, and what I mean specifically is we want to calculate the head. The head, the H sub D, is the elevation at D, and the velocity head at D, and the pressure head at D. So we want to know how much energy is there at D. And if the amount of energy that there is at D is more than the elevation of the water at A, then which way would the water be flowing? From D towards A. But if there's less energy at D than the elevation of the water at A, then the water flows from A towards D. So that's what this whole analysis is built around, is us trying to figure out how much energy there is at D. And we're going to use an approach that by now I think is starting to seem familiar to you. We're going to have too many unknowns to actually start calculating, and so we're going to begin with a guess. We'll just pick some number, do some calculations, and see where that gets us, and then we may need to adjust our guess based on what we find out on the basis of that initial guess. And so we're going to make little adjustments until it's clear that we have convergence. Convergence is just the notion that things have stabilized, that you're seeing equilibrium where there ought to be equilibrium. So that's going to be the method that we're working with. We're going to have certain pipes where we know the flow rate. We know the water is going out from B in towards C, but the middle reservoir, we're not so sure which direction the water is flowing because initially we don't know how much energy there is at D. What direction is that water flowing? How much flow is there through each pipe is part of this three reservoirs problem. You know, the flow rate, Q, is going to be unknown. Even if we know the direction from B to D, we don't yet know the flow rate until we've gone through this calculation process. So we want to establish that. And then once we know the flow rates, we could calculate the pressure at the junction if we know the elevation at the junction. If we know its physical height above some datum, then we can use the head that we've calculated and the velocity that we know to calculate the pressure at the junction. Okay. So the basic principle, water flows out of the high reservoir into the low reservoir, and the middle one, it depends on how much energy there is at D. And so the difference in head at each end of the pipe is going to be what we're analyzing. And the slope of the energy grade line, S sub F, we're going to, one of the columns in our spreadsheet is going to be calculating the slope of the energy grade line. And that's going to be, same as it always has been, the head loss due to pipe friction divided by the length of the pipe. And of course, here is the Hazen-Williams equation. If we know the slope of the energy grade line, and for a certain circular pipe, we can calculate the hydraulic radius, and for a certain pipe material, we'll know the C value, and then this 1.318 is just a correction factor. We're going to get the flow velocity through the pipe by this estimation of the slope of the energy grade line. And what we're looking for is we want to make sure that here at junction D, the flow in and the flow out are equal. That's the continuity principle. that's our convergence criteria. The way that we know that we're done calculating is when the flow in to junction D and the flow out of junction D is in balance. Okay, so here's the problem. The template file that you can find available on Blackboard, let me open that up. It is this student start. It's got a pictorial summary of the problem here as well. So let's just analyze what we know. Okay, the water in the elevated pipe is at 85 feet. We're calling elevated reservoir. This is reservoir P. It's flowing through 600 feet of 12-inch diameter plastic pipe, C value 150. So first of all, compare this pipe to the other pipes. It's short, it's a big diameter, and it's smooth. So water's going to flow through pipe PR pretty easily. Water in the other pipes, though, the pipes are longer, smaller diameter, and the material is more rough. So there's relatively little resistance to flow through pipe PR, and there's relatively more resistance to flow through RT and RM. So we'll keep that filed in the back of our mind for later when we're just analyzing the situation. But we know that the water's going from P to R. You can see the direction here has been specified from R towards T, but the flow from R to M, we don't know if the water's going into that reservoir or out of that reservoir. We haven't done the calculations yet. Okay, so here is the Hazen-Williams equation to solve for the flow velocity. Any questions so far just about the overall concept? Does everybody get why we're so perplexed here? Why we don't know what the flow rate is yet? We don't know the magnitude because, well, for one thing, we haven't done any calculations for the magnitude, but what complicates things is just that we've got a split flow situation. So I'm going to show you how to handle that split flow situation. Okay, so here's kind of the framework for what we're going to solve. Just starting in the first column, we're going to begin filling in details about the pipe. And so let's begin with that. The first line is pipe P-R, and I'll name the pipe just based on where it's going from and where it's going to. So from P towards R, the pipe material is plastic. The C value that we can get from the diagram, that roughness coefficient is 150. You can see that the length of the pipe is 600 feet. The diameter of the pipe in terms of feet, so it's reported in inches. Here it wants it in feet, so I'm just going to say 1 foot diameter. Okay, now I have to calculate the area. Pi times d squared divided by 4. So that's the cross-sectional area of the pipe. Let me type in the other pipe material before I start with this guess thing. So there's also pipe MR. Now I don't know what direction, whether it's going from M towards R, or from R towards M. So I won't get hung up on that. I'm just naming it. It's cast iron. The C value is 130. The length of this pipe MR is 1,300 feet. Its diameter is 6 inches, so equals 6 divided by 12. That's half a foot diameter. And I can just drag the formula down for the area. I don't have to type that in again. I just click and drag, and it calculates the cross-sectional area for me. Our third and final pipe is T-R. And this one is galvanized iron with a roughness factor of 120, a length 1350, diameter is 8 inches, so equals 8 divided by 12. And once again, I'm just going to apply the formula from above to calculate the area. Okay, now what should be our first guess of how much energy there is at R? It would be a bad guess if I said that there's 90 feet of energy at R. Because if there's 90 feet of energy at R, then that's going to mean that water has to flow from R towards P, like water would be going out in all directions. And so that would be like an impossibility. Your guess has to be below the highest reservoir and above the lowest reservoir. So our possible guesses can be anything beneath 85 and anything above 15. So I'm just going to guess as a starting point 50 feet. We'll analyze this situation based on a guess of 50 feet. And so below this, the cell below this, I'm going to just equals and look up at the previous one. So if I change it, I don't have to change it in 3 different spots. So equals, just look at the one above. And that way, if I decide to go for 49, see how it changes all of them instantaneously? 46. Let's go back to 50 though. Okay, so if there is 50 feet of energy at R, what direction is the flow going? Is it going from M towards R, or is it going the other way if there's 50 meters of head at R? I'm sorry, feet. If there's 50 feet of head at R, what direction is the flow? Garrett? You seem like you know this one.
Towards M and towards T.
Towards M and towards T. Good. You're exactly right. So over here, when we have in and out, in is if the water is coming into the junction. So for example, as it's pictured here, PR is flowing into junction R. Because of this arrow is going out of junction R, Q of RT is out. So we're going to keep track of the ins and the outs later on based on this initial guess. So what about head loss? If at P there was 85 feet of head at one end of the pipe, and now there's 50 at R, then the head loss through pipe PR would have to be 85 minus however much head there is at the end. So it was 85 was how much head was at the beginning of the pipe, and there's 50 feet of head at the outlet of the pipe. So if there's 50 feet of head at R, then that means there was 35 feet of head loss through this pipe because it started at 85 and it ended at 50. So just therefore it's 35. MR. If it's 50 here and it's going to 20, you can see that would be 30 feet of head. So it is 50 minus 20. And if we have 50 feet of head here and we're going to 15, it's 50 minus 15, 35 feet of head. So if we change this guess, like if we said maybe 70, all the other guesses are going to change accordingly as we adjust our guess, which I'll put back to 50 now. Okay, do I need to repeat any of the stuff that I've done so far? We do have time for questions if anybody's got questions, so don't be shy. I want you to understand this. Okay, head loss, S sub F. Remember the formula for S sub F is H sub F divided by L. The slope is the magnitude of head loss divided by the length of the pipe. So it is the magnitude of the head loss divided by the length of the pipe. We can drag that formula down for all of them. Velocity, we're going to use the Hazen-Williams equation, equals 1.318 times C times the hydraulic radius. So for hydraulic radius, remember if this is a circular conduit that's flowing full, the hydraulic radius is d divided by 4. So I'm going to just click on the diameter, divide by 4, and then when I close the parentheses, I now need to take it to the power of 0.63. And then finally multiplying it by the slope of the energy grade line. Now, since this is, my formula is centered, I can't click on the location. See, I want to click on I-27. I can't click on I-27 because my formula is in the way. So that just forces me to type I-27. I can't click on it, but that's all right. Not the end of the world. To the power of 0.54. Okay, so the water velocity will be 17.8 feet per second if, the big if that all of this hinges on, is if there's 15 feet of head at location R. We don't know yet whether that's a good guess or not. We're going to evaluate the quality of that guess in just a moment. But so far we've got the velocity based on this contingency. And let me drag the formula down through the other two cells. And it'll calculate the velocity, you know, for pipe MR if this is the slope of the energy grade line, and for the diameter that's specified. So all of these formulas are looking at the particular C value, the particular diameter, and the slope of the energy grade line for that pipe. Okay? So PR, in this assumption, the water is flowing into the junction from pipe PR, and the water is flowing out from the junction through MR and out through the junction using pipe TR. Okay, so in is just because the water's coming into the junction. Like if we were to draw just a little control surface or a control volume and see, like at this node R, is the water coming in or out through a given pipe? It's coming in through pipe PR and out through the other two. Q equals VA, so velocity times area. And we can apply that formula down through all three of the rows. Okay, so now the question is, comparing in and out. We want to have out minus in this cell. Okay, so out minus in equals, here is an out, and here is an out. So that's the combined outflows, and then subtract the inflow. Out, the combined outflows minus the combined inflows. So the fact that this isn't 0 tells me that my guess wasn't perfect. I need to adjust my guess. And in fact, we can do better than just blindly pick a different one. We can know whether the guess that I made before was too high or too low. Now look, one of these is way bigger than the others. This in is larger than it should be. So the conclusion, the way to diagnose whether our initial guess was too high or too low, if the combined outflows are bigger than the inflows, then that tells you that the guess of TR was too high. And so the other way of writing that, let me write the opposite of that statement on the whiteboard. Sometimes these logical statements are hard to see in the heat of the moment. If Q in is greater than Q out, then guess of head at the junction, in this case the junction is called location R, then the head at location R is too low. So that I swapped it. The statement on here says if out is bigger than in, the guess is too high. That didn't apply to us because for us, in is bigger than out. So if in is bigger than out, then your initial guess of the head, how much energy there was at R, our initial guess was too low. So let's just look and see if this becomes closer to 0 by raising it from 50 to something else. So we want this to be 0. So what about 51? Yeah, that went in the right direction. It's less negative now. Okay, I'm going to leave it for iteration 1. Like, if you're kind of an Excel wizard, you probably already know where this is heading, and you could just solve it all here at once in one row. But let's show our work by, having our initial guess, and let's just copy everything in iteration down to iteration 2. So highlight. Why does it keep? There's something wrong with this computer. I tell you, it's haunted. Every time I click on one cell, it actually goes to a different cell. Okay, so highlight all of these and Control-C and Control-V to paste. Let's just make sure everything, it looks the same. The reason why I suggest that we change it is I want us to be able to see this initial stage when it wasn't balanced. And so down here I'm going to say, since Q in is greater than Q out, we must, well, let me do it this way. Our first guess of HR was too low, so let's raise the guess for the next step. All right, so I wanted to preserve kind of showing the flow of the solution, and then we'll make the change down here in iteration 2. So before I start optimizing this guess, any questions about the analysis part of it? Well, how do we know, like, where did this come from? If out versus in, too low. Think about, what if there was a hole in this pipe? Like, what if there was a hole in the junction, of water pouring out of that junction? If you raised the junction, water would be pouring out of it less. So, like, the fact that there's so much flow through QPR, if there's a lot of flow, that means raise the junction, that'll slow it down. Just think about, like, if you've got a pipe connected to the reservoir and the reservoir is open, just water shooting out. Okay, if I told you the water's going out of this pipe too fast, all you have to do is just raise that end of the pipe a little bit, and then it won't go out as fast. So now, if it's here, then it's going to be coming out less fast. So you need to just raise the estimate of where this pipe terminates, and that's going to slow down the flow. So in this first iteration, there's too much coming into the junction. There's too much going through PR. We know that there's too much because however much is coming out of that pipe has to also be coming out through MR and TR. So in and out have to be equal. The whole continuity principle is that if there's a junction where 3 pipes come together, the flow into the junction and the flow out of the junction have to be in balance. And so right now it's not in balance because there's just too much water going through that top pipe. So why are we going to raise the estimate? It's just we don't want there to be so much of a slope between P and R. We want to raise the location of R by increasing our estimate of the head. Okay, so in practical terms, we could try 51. That's getting better. 52. Still better yet? 53. 54. This is getting tedious. 55. So we go here into the Data tab. Look for the What If analysis and Goal Seek. And what we're going to do is we're going to tell Excel our objective here is for this cell to be equal to 0. and then it can change this cell, which is the guess, and as long as it changes that one, these other two are also going to change as a reflection of that. And OK. And very quickly it finds that the amount of head that there is at junction D, which causes a balance of the inflow and the outflow, is for there to be 79.452 feet. Okay. So any questions? Well, let me ask you a question. How would this have all been different if we were using Darcy-Weisbach instead of Hazen-Williams equation? Why did Hazen-Williams make this a little bit easier? What's easier about the Hazen-Williams equation than Darcy-Weisbach? Something about the friction factor. That's right. Pardon me?
Oh, yeah, we just used this.
With Hazen-Williams, we have a constant friction factor. What about in Darcy-Weisbach? What does the friction factor depend on? Diameter is one of the terms. Type of material is another.
Reynolds number.
What's the one that's always causing us the trouble? It's the Reynolds number, because like until now, in a few occasions, we didn't know what the flow rate was yet, and so we can't know the F value until we know the flow rate. We don't know the flow rate because we don't know the F value. That whole conundrum. Well, think about this problem. We didn't know what the flow rate through the pipes is going to be. So on Friday, the lecture is going to show you how to handle the three reservoir problem with Darcy-Weisbach. There's a way around it. We just have to start with a guess. But this made it a little bit simpler for us because the C values were constant. So our solution iterates more quickly than it will for the Darcy-Weisbach equation.
Can the error not be 0? Does it have to be as close to 0?
Not be 0.
You put 0.001.
Yeah. If we wanted it to be more accurate, instead of using goal-seek, we could use solver. And solver forces the solution to be, this is accurate to, if you look at the guess that it's found, accurate to this many digits. Solver would force it to be even a little bit more accurate. But for our purposes, this is close enough. We will get into solver later for other applications where we need it to really converge perfectly, but we're not going to do it for this one. Go ahead.
So what, on the first iteration it's H sub R, on the second one it's H sub D.
Yeah, sorry about that. That's just that's a mistake. It should see H sub R for both of them. I modified a previous example, so if I can get this to stop. I clicked on the solver button and now it won't let me quit. It wants to solve something. I woke it up. It's like when you summon a vampire. Okay, we're all done. Ugh. Objective cell must be on the active sheet. Okay, objective cell. Okay, how about this one? Close. All right, it'll let me close it. Yeah, so change this to R, H sub R. Because it means like the junction where three things come together. The reason why it said D is the example that we're going to see on Friday. That junction is named D. So I adapted the spreadsheet to Hazen-Williams. Other questions? All right, now what if we wanted to know the pressure at R? That is part of this example. Now that we found the flow rates, then what is the pressure at location R if we know the elevation is 35 feet? Okay, so down here, we know that the head at R, we've just calculated, is 79.45. The elevation at location R is 35 feet. Now velocity head. Water is flowing through three different pipes. A large diameter pipe, a small diameter pipe, and a medium diameter pipe. And so this junction at R, you know, there is some energy tied up as a velocity head. I'm going to find the average velocity head and just assume that that's it. So I need to find the velocity head through pipe PR. So that is the velocity in pipe PR, V squared divided by 2G, 2 times 32.2. So velocity head is V squared divided by 2G. So I'm just going to find the velocity head in each of those three pipes. That was for pipe PR. For MR, I think I can just drag this down through those. And then the average of these. And so how much energy is in the velocity head? Not a lot. Like 1.12 feet of head is tied up as velocity head. Now here's our definition of head. Head is pressure head, elevation head, and velocity head. So we want to know the pressure at location R. Pretend that doesn't say D. The pressure at location R is the head at R minus the elevation at R minus the average velocity head at R, and then multiplied by the unit weight of water. Okay, so the pressure at R is the head at R. The head is all the total energy minus the elevation minus the average velocity head, and then multiply that by the unit weight of water, 62.37 pounds of force per cubic feet. Need to put the star in to multiply. Okay. So 2702 pounds per cubic foot. And then how do we get PSI from that? Divide by 144, because if you've got 2,700 pounds on a cubic foot, then on just 1 cubic inch is going to, per square foot, a square inch is going to have much less than that. We have to divide by 12 and divide by 12. So it is this pressure divided by 144. So the pressure at that junction, 18.7 psi. So we can say this is how much pressure there is at junction R, since the elevation at R is 35 feet. Okay, so if you didn't have your computer with you today, my recommendation is to get the template file, and when you're at home tonight, try and work through this example so that you've got this available. If we look at the homework assignment that's due next week, problem 3 is create your own three reservoirs problem that incorporates the Hazen-Williams equation. Prepare a sketch, a table of pipe characteristics, and calculate the solution for the problem you've created. So basically, you can just use this to make your own problem. You know, name the reservoir something, give them some elevation, choose a pipe length, choose a pipe material type, but basically, once you've got it solved one time, if you create an example of your own, then that'll help to reinforce the method. Yeah?
If this problem was on the exam, are we allowed to use this template, or would we have to make
Good question. So the question was, for the exam, you need to start with a blank workbook on the exams. You can't use the templates that I provided, and you can't use your previously solved homework assignments. And so for an Excel problem, what you can do, since you're going to be allowed to make your own formula sheets on the exam, you can remind yourself what the column headings should be. So, you know, like you could say for a three reservoirs problem with Hazen-Williams, you should have the name, material, C value, L. So you could kind of give yourself enough reminders that you could very quickly create the spreadsheet from your blank workbook. That's a good question. I'm glad that you asked that. All right, so just to reiterate, the homework is due on Wednesday, but then class on Friday is online. So I'm going to be showing you the next example through a recording. I wish we could do it together, But this Darcy-Wiesbach Three Reservoirs Problem, that's what we're going to be going through on the recorded lecture for Wednesday. I'm sorry, for Friday of this week. And then the binder check on Monday. So if you have any questions as you're working on it, feel free to come see me in my office or give me a call or send me an email and I'll be glad to help you out. I'll see you on Monday.